In the last lesson, we studied the limits of a function. Once you understand how limits are used in functions, the next step is to learn how limits explain the computation of the slope at any point of a non-linear function. Like it was explained before, differential calculus equals a slope finding. Now, because finding limits to get to the slope is a slow and tedious process, and this being math, the derivative is nothing more than a very quick way to find the slope at any point of a curve, if we know the equation of the curve. This means, of course, that because we have so many different equations for curves, we have to make sure we are using the derivative correctly when we attempt to find the slope. Previously, we used the tangent to a parabola to find the slope at a point. We did it by finding the slope of secants until the secant became a tangent. Well, now we will use the same approach to derive a quick fix to find the slope. Again, we use the same old change of y over the change of x equation to find the slope. But this time we will take aim at the instantaneous or the smallest rate of change, or like they say, as the value of the change of x approaches 0, to find the average rate of change without turning into 0, of course. Okay, the change of y over the change of x. Now, some books will call y the function of x, or f of x. It doesn't matter which notation we use. Notation has nothing to do with the process. Anyway, the change of the function of x over the change of x. But this time we will take into consideration the shift in the curve, which we will call h. H is not a new variable. H is just the incremental amount of x or y. So the equation for the slope will have this added h shift, and the rate is equal to the function of x plus the shift h, minus the function of x. In other words, this is the change of the vertical axis y. In the denominator, we increase x by the h amount, but because we have to find the difference, the value of the original x gets subtracted, leaving h by itself in the denominator. This is the equation called the derivative of the function. If we want to find the slope of a function at any point, we may use this equation. Notice the notation for the derivative, f prime of x. In a way, we have gone from a secant to a tangent without knowing it. You will see in a moment how the shift becomes irrelevant using limits without having to resort to 0. Okay, now let's try this example. What is the derivative of the function x cubed? Using this newfound equation gives us the limit as h approaches 0. We place the function into the equation like this: x plus h cubed minus x cubed over h. We multiply x plus h by itself once and get x squared plus 2xh plus h squared. We do it again because it is cubed and get x cubed plus 3x squared h plus 3xh squared plus h cubed. We continue by subtracting x cubed, divided, of course, by h. Both x cubed cancel, and the h in the trinomial gets factored out. The factor h cancels with the h in the denominator. We are left with 3x squared plus 3xh plus h squared. Now, because we want the limit of h approaching 0, h becomes 0 and the outcome is 3x squared. What has happened is that by taking the incremental value of h to an instantaneous 0 level, we have derived an equation that will give us the slope at any point in the curve represented by the equation x cubed. What a trick! No wonder we have been calling Newton a genius for over 300 years. So if we want the slope when x equals 1, we solve the derivative 3x squared for 1. 1 squared times 3 is 3. The slope of the curve when x equals 1 is 3. If we want to find the slope at 2, 2 squared times 3 is 12. So the slope is 12 when x in the curve is 2. The table shows the different values of the slope for different values of x. This is the end of the first part of the derivative. In the second part of the derivative, a couple of more examples will be shown, and then the real easy shortcuts to differentiate equations will be demonstrated. In the third and last part, various examples of differentiation will be explained.